Okay, so here's my example for the data that I got for lab 7 problem 1. So this just shows the y versus t graph of the mass going up and down. So I tried my best to make sure that the mass was at 0 near its equilibrium position. So what I did is I found where the equilibrium position was, and then it was around 44 or 45. I think it is 40. It was 45. Um, and then went up to 40. So then it would go down between 40 and 50. Um, so the reason why I wanted to do that is because I wanted to make this look like a sine wave. So the one thing that you should notice is that I actually got to start um, at t equals 0 when the mass was going down. So this actually ended up being negative sign. Um, so if I really wanted to make it a sine wave, I would have gone back and made sure to set it 0 when it was going up. But I kind of just looked for the first instant when it was like around 45. So then that's obviously when it's going to be going down. Anyway, um, so this will actually help you a lot with your extra credit project, going over kind of what's going on. So I fit this, as you can see, it looks like a negative sign, and I fit this in Motion Lab. And I have the following parameters. So I set it as, a sine function. The first interesting thing is that a equals -1. So that's just the offset in the sine wave. So instead of it being, centered at 0, it's centered at -1 here. So that's probably just because I didn't have the mass at perfectly the equilibrium position. So this is kind of irrelevant for what we want to find. The most important thing is going to be the c, since it's multiplied by z, which was, which is kind of funny that it says z, but z is actually t, the thing that's plotted on this axis. So that's going to be so z is here, and then c is going to be our omega. So c is going to be what we're going to want to look for. So the first thing, so another thing, I guess. Um, b is -5.7. So you can look to see, well, there's a little offset. I have a equals -1. So -1 plus -5.7. And it looks like at the negative end it's around 6.7. Um, okay. So and then at the positive end you're gonna have -1, and then plus 5.7. And as you can see, this is around -4.7. So that's kind of a trick to fit your amplitude of the graph. And then the most important thing, c, which is omega, which we want to find here, because we can find omega, then convert it into, or find omega, convert it into frequency, see if it fits our prediction equation, yada yada yada. So we got c is 7.8. Now let's see if that makes sense. So a period occurs from, you can measure it here, from trough to trough of the sine wave. So at this trough, it looks like it almost occurs exactly at 1. And then this trough here looks like it occurs around around point 0.2. So we can say that the period is about 0.8 seconds. So if the period is about 0.8 seconds, the frequency is about 1 divided by 0.8 seconds. And 1 divided by 0.8 is 1.25. So 1.25 is going to be the frequency. So there's 1.25 cycles every second. Um, so that's f, but we want to find omega, and we know that omega is 2 pi f. So we're going to multiply 1.25 times 2, and then multiply that by 3.14. And then if you do that, you'll notice that we get 0.785. And notice how here I fit c as 0.78, so that's pretty close. So basically the take-home message here is that c is the angular frequency that we want to find, and you can do these little tricks to help you fit your graph.